The closest star to our Sun is only 4.24 light-years away. That word "only" is the most dangerous lie in astronomy, because 4.24 light-years is 25 trillion miles. If you loaded a crew onto the fastest interstellar probe ever launched and aimed it directly at Proxima Centauri, that crew would be dead for over 70,000 years before the ship arrived. And that is the easy part. The real nightmare begins when you try to solve every problem between here and there. Radiation that shreds human DNA. Engines that cannot carry enough fuel to stop. Life support systems that must run flawlessly for longer than most civilizations survive. The terrifying truth is not that the stars are far. It is that even the nearest one may still be too far for us. If you enjoy deep dives into the realities of space that most people never hear about, then consider tapping that like and subscribe button. It helps more than you know, and I genuinely appreciate every single one of you. Now, get yourself comfortable. Let's begin. On August 24th, 2016, the European Southern Observatory held a press conference that changed the trajectory of human ambition. Scientists announced they had found a planet orbiting Proxima Centauri, the nearest star to our Sun. Not a gas giant, not a frozen wasteland spinning in the outer dark. A rocky world, roughly the mass of Earth, sitting inside the habitable zone where liquid water could theoretically exist on its surface. They named it Proxima Centauri b. The discovery electrified the scientific community and captured headlines worldwide. An Earth-sized planet orbiting the closest star. The language practically writes itself. The nearest potentially habitable world, right next door, almost within reach. The news felt like destiny, as if the universe had placed a second Earth at the shortest possible distance and dared us to go get it. For anyone who had ever stared at the night sky and wondered whether humanity might someday walk beneath alien stars, Proxima b seemed like an answer. Not a vague promise buried in some impossibly distant galaxy, but a concrete destination attached to the very nearest star, a place we could name, study, and point a telescope toward. A world close enough that the light reflecting off its surface left only 4 years and 3 months ago. But there is a difference between a destination you can name and a destination you can reach. And the distance between those two ideas is where this story turns from inspiration into something far more unsettling. Proxima Centauri is a red dwarf star located 4.24 light-years from Earth. It is the closest star to our solar system, part of the Alpha Centauri triple star system that dominates the southern constellation Centaurus. The system contains 3 stars. Alpha Centauri A is a yellow star slightly larger and brighter than our Sun. Alpha Centauri B is an orange star, somewhat smaller and cooler. These two form a close binary pair, orbiting each other every 79.9 years at distances ranging from roughly 11 to 36 astronomical units apart. The third member, Proxima Centauri, is a dim red dwarf with only about 12% of our Sun's mass and roughly 14% of its diameter. It orbits the central binary pair at an enormous distance of approximately 13,000 astronomical units, taking over 500,000 years to complete a single orbit. Proxima sits slightly closer to us than its 2 brighter companions, making it the nearest individual star to our solar system by a slim margin. The discovery of Proxima Centauri b was not an accident. It was the product of years of careful observation using a technique called Doppler spectroscopy. As a planet orbits its star, its gravitational pull causes the star to wobble very slightly. That wobble shifts the star's light toward red as it moves away from us, and toward blue as it approaches. By measuring these minuscule shifts in Proxima Centauri's light spectrum over months and years, astronomers at the European Southern Observatory detected a repeating signal with a period of approximately 11.2 Earth days. That signal corresponded to a planet with a minimum mass of about 1.07 times Earth's mass, orbiting at a distance of roughly 7.25 million kilometers from its star. Because Proxima Centauri is so much dimmer and cooler than our Sun, That close orbit places the planet within the habitable zone, the region where temperatures could allow liquid water to persist on a rocky surface. Since the initial discovery, additional planets have been identified in the system. Proxima d, a sub-Earth mass planet orbiting even closer to the star, was confirmed in 2022. A candidate planet called Proxima c was reported in 2020, but its existence remains disputed due to potential artifacts in the data. The system is still being studied, and the exact properties of Proxima b remain uncertain. We do not yet know whether it has an atmosphere, whether it has a magnetic field strong enough to protect that atmosphere, or whether the intense stellar flares characteristic of red dwarf stars have stripped the planet bare. Proxima Centauri is an active flare star, periodically releasing bursts of ultraviolet and X-ray radiation that could be devastating to any exposed surface. Whether Proxima b is a living world, a scorched rock, or something in between remains an open question, but none of that changes the fundamental fact that captured the world's attention. There is an Earth-mass planet in the habitable zone of the nearest star. It is the closest known exoplanet to our solar system, and the temptation to call it reachable is almost irresistible. 4.24 light-years. Say it fast and it sounds manageable, like a number you might encounter on a road sign or a shipping estimate. 4.24. The decimal point makes it feel precise, contained, almost modest. Compared to the scale of the galaxy, it is modest. The Milky Way stretches roughly 100,000 light-years across. The nearest large galaxy, Andromeda, lies 2.5 million light-years away. Against that backdrop, 4.24 light-years looks like a rounding error, a single step on a staircase that extends to the roof of the universe. But a light-year is not a unit designed for human intuition. A light-year is the distance that light travels in 1 year, moving at 299,792 kilometers per second. In 1 second, light crosses a distance roughly equivalent to circling the Earth 7.5 times. In 1 minute, it reaches past the orbit of Mars. In 8 minutes, it arrives at the Sun. In about 5.5 hours, it passes the orbit of Pluto. But then the scale changes. After passing the outermost objects in our solar system, light enters interstellar space, and the next landmark is Proxima Centauri. The light leaving our Sun right now will not arrive at Proxima Centauri for 4 years, 2 months, and roughly 17 days. 1 light-year equals approximately 9.46 trillion kilometers. Multiply that by 4.24 and you get the distance to the nearest star, approximately 40 trillion kilometers. Written in miles, roughly 25 trillion. Written in astronomical units, the standard measure of distance within our solar system, where 1 AU equals the distance from Earth to the Sun, Proxima Centauri lies approximately 268,770 AU away. That is 268,770 times the distance between Earth and the Sun. To understand what that number means in physical terms, rather than mathematical abstractions, consider the following. The Voyager 1 spacecraft, launched in 1977, is the most distant human-made object in existence. After nearly 5 decades of continuous flight, it has travelled roughly 165 AU from Earth. It moves through interstellar space at approximately 17.3 kilometers per second, which is about 62,000 kilometers per hour. At that velocity, Voyager 1 covers roughly 550 million kilometers per year. That sounds impressive until you measure it against the distance to Proxima Centauri. At Voyager 1's current speed, the journey would take approximately 73,000 years. To put 73,000 years into human perspective, that is roughly 10 times longer than all of recorded civilization. When Voyager 1 hypothetically arrived at Proxima Centauri, the entire history of writing, agriculture, cities, empires, science, industry, and spaceflight would fit inside barely the first 15% of the journey timeline. Now consider the Parker Solar Probe, the fastest spacecraft humans have ever built. During its closest approaches to the Sun, Parker reaches speeds of approximately 191 kilometers per second, roughly 690,000 kilometers per hour. That is fast enough to travel from New York to Los Angeles in about 20 seconds. At Parker's maximum velocity, the trip to Proxima Centauri would take approximately 6,700 years, faster than Voyager by an order of magnitude, still longer than the span of time separating us from the construction of the Great Pyramid at Giza, still longer than the entire history of ancient Egypt, Greece, Rome, the Middle Ages, the Renaissance, the Industrial Revolution, and the Space Age combined, repeated 3 times over. And Parker Solar Probe achieves that speed only during its closest approaches to the Sun, when its highly elliptical orbit carries it briefly through the solar corona at maximum velocity. No spacecraft maintains anything near that speed in open interstellar space. No propulsion system currently in operation can sustain such velocities over the distances required. These are not abstract numbers. They are engineering realities that define the boundary between what humanity has accomplished and what the nearest star demands. We have sent probes past every planet in our solar system. We have landed machines on Mars, on Titan, on a comet. We have driven rovers across the Martian surface for years at a time. Every one of those achievements occurred within a radius of roughly 50 AU from Earth. The nearest star sits at 268,000 AU. The gap between our farthest achievement and our nearest stellar destination is not a gap. It is a chasm so wide that every unit of distance humanity has ever crossed fits inside it thousands of times over. The Alpha Centauri system has been a target of scientific fascination long before the discovery of Proxima b. Alpha Centauri A and B are among the most studied stars in the sky, partly because of their proximity and partly because they are similar enough to our Sun to suggest the possibility of habitable planets. Alpha Centauri A is a G-type main sequence star, the same spectral class as the Sun, about 10% more massive and roughly 50% more luminous. Alpha Centauri B is a K-type star, slightly cooler and dimmer. Together, they form one of the best characterized binary systems in astronomy. Proxima Centauri, by contrast, is far smaller and dimmer. It emits only about 1/1600% of the Sun's luminosity. You could not see it with the naked eye despite it being the closest star to Earth. Its faintness is the reason it was not discovered until 1915 by astronomer Robert Innes at the Union Observatory in South Africa. The 3 stars are gravitationally bound but separated by enormous distances. Alpha Centauri A and B orbit each other relatively closely, but Proxima Centauri orbits the pair at a distance so vast that some astronomers questioned for decades whether it was truly bound to the system or merely passing through the same region of space. Observations confirmed the gravitational association, but the sheer scale of the system underscores a point that becomes critical as this story progresses. Even within a single star system, distances can be staggering. Proxima Centauri orbits its companions at roughly 13,000 AU. Our entire solar system out to the orbit of Neptune fits within about 30 AU. The Alpha Centauri system is a reminder that even local neighborhoods in space operate at scales that dwarf human experience. The excitement surrounding Proxima Centauri b is understandable and scientifically legitimate. Finding an Earth-mass planet in the habitable zone of the nearest star is one of the most significant discoveries in the history of exoplanet science. It means the closest possible target for interstellar exploration is not merely a star, but a star with a world that might, under the right conditions, support liquid water. Every major space agency and dozens of independent research groups have studied or proposed missions to the Alpha Centauri system, specifically because of this combination of proximity and scientific interest. But proximity is relative, and the word nearest performs a kind of psychological magic that obscures the physical reality it describes. When we say Proxima Centauri is the nearest star, we are making a statement about ranking, not about accessibility. It is the closest among hundreds of billions of stars in the Milky Way. being first on that list does not mean it is close in any sense that human engineering currently recognizes. Imagine standing at the edge of the Pacific Ocean and being told that the nearest land across the water is 5,000 miles away. You could accurately call that the nearest point. You could reasonably dream of reaching it, but standing on the shore with no boat, no fuel, and no proven means of surviving the crossing, the word nearest starts to feel less like comfort and more like a taunt. The psychological effect of the word nearest compounds when combined with the discovery of Proxima b. Suddenly the destination is not just a star but a world, and not just any world but one that might resemble Earth. The human mind, shaped by millions of years of terrestrial exploration, pattern matches this to every frontier we have ever crossed. We crossed oceans, we reached the poles, we walked on the moon. Surely the nearest star is just the next challenge in that progression. What this intuition misses is that every previous frontier existed within the same gravitational neighborhood. The moon is 1.3 light seconds away. Mars, at its closest, is about 3 light minutes away. The Voyager probes, the farthest objects we have ever sent, are about 22 light hours from Earth. Proxima Centauri is 4.24 light years away. The jump from light hours to light years is not the next step on a smooth curve. It is a vertical cliff face in the graph of distance, a discontinuity so severe that every tool and technique that carried us through the solar system breaks down against it. Consider the energy requirements alone. The kinetic energy of a moving object scales with the square of its velocity. To double your speed, you need 4 times the energy. To reach 10% of the speed of light, roughly 30,000 kilometers per second, a spacecraft would need to achieve a velocity approximately 1,700 times greater than Voyager 1's current speed. The energy required to accelerate even a modest payload to that velocity is not merely large. It is comparable to the total annual energy consumption of entire nations. And that calculation assumes perfect efficiency. No energy lost to heat, no mass penalty for fuel, no reserves for course corrections or deceleration. In practice, the numbers get worse. Much worse. The rocket equation, formulated by Konstantin Tsiolkovsky in 1897, describes the fundamental relationship between a rocket's exhaust velocity, its fuel mass, and the speed it can achieve. The equation is exponential. For any given exhaust velocity, increasing the desired speed requires an exponential increase in fuel mass. Chemical rockets, which have exhaust velocities of roughly 3 to 4.5 kilometers per second, hit a practical wall long before reaching the speeds needed for interstellar travel. Even nuclear thermal rockets, with exhaust velocities roughly twice those of chemical rockets, cannot overcome the exponential tyranny of the rocket equation at interstellar scales. The fuel mass required to accelerate a meaningful payload to even a few % of light speed using any conventional rocket exceeds the mass of the payload by factors of thousands or millions, depending on the technology. This is not a budget problem or a political will problem. It is a physics problem, embedded in the mathematics of propulsion. Every kilogram of fuel you add to a spacecraft increases the total mass that must be accelerated, which demands more fuel, which adds more mass. The equation spirals. At some point, no amount of fuel gets you where you need to go because the fuel itself becomes the primary burden. This exponential trap is the reason that every serious interstellar propulsion concept abandons conventional rocketry entirely and reaches for something exotic: nuclear pulse propulsion, fusion drives, antimatter engines, laser-pushed sails. Each represents a fundamentally different approach to the problem, an attempt to break free of the rocket equation by using fuel with dramatically higher energy density, or by leaving the fuel behind entirely. But even the most promising of these concepts, the ones that occupy serious engineering studies rather than speculative fiction, produce travel times measured in decades at minimum and centuries at maximum for a journey to Proxima Centauri. Not one of them has been built. Not one of them has been tested at scale. Not one of them currently exists as anything more than calculations, computer simulations, and small laboratory prototypes. The distance to the nearest star does not merely challenge our current technology. It challenges the next several generations of technology that we have not yet invented. There is a way to make the distance to Proxima Centauri feel visceral rather than abstract. Imagine shrinking the Sun to the size of a basketball. At that scale, Earth would be a small grain of sand, orbiting about 26 meters away. Jupiter would be a marble, roughly 135 meters from the basketball. Neptune, the outermost major planet, would be a slightly smaller marble orbiting about 800 meters away. The entire solar system out to Neptune fits within a sphere roughly 1.6 kilometers in diameter. Voyager 1, the farthest human-made object, would be about 4 1/3 kilometers from the basketball. Now, at that same scale, where would Proxima Centauri be? Not across the room, not across the city, not across the country. Proxima Centauri, scaled down proportionally, would be another ball sitting approximately 6,900 kilometers away. That is roughly the distance from London to New Delhi. The entire solar system, everything humanity has ever explored or sent a probe to, fits within a 2-kilometer radius. The nearest star is nearly 7,000 kilometers away at that same scale. Every spacecraft we have ever built is still in the front yard. The nearest star is on the other side of the planet. That is what 4.24 light-years looks like when you strip away the comfortable abstraction of the number and force it into a scale the human mind can attempt to process. And this is the nearest star. Not a particularly interesting one, not a particularly promising one, just the one that happens to be closest. Everything else in the galaxy is farther. Most of it is incomparably farther. If this is the shortest possible interstellar journey, and this is what it demands, then the question is no longer whether Proxima Centauri exists as a destination. The question is whether any propulsion system humans can realistically build will ever close that gap. Because right now, the fastest spacecraft in history would need thousands of years to make the crossing. And the technologies that could theoretically cut that timeline down to decades have never left a laboratory, a whiteboard, or a computer screen. Some of them, as of 2025, have not even maintained their funding. Even the most ambitious interstellar propulsion initiative ever funded, Breakthrough Starshot, aimed only to send gram-scale chips on a one-way flyby, not a crewed mission. Not a vessel that could slow down and orbit, not a ship carrying human beings who need to eat, breathe, and survive. Just a tiny chip with a camera, flung past the nearest star at 20% of light speed, returning a few snapshots during a flyby lasting hours. And as we will see, even that stripped-down vision has collided with engineering realities that no amount of ambition could shortcut. The nearest star is 4.24 light-years away. It has an Earth-mass planet in the habitable zone. Everything about that sentence sounds like the opening chapter of a story where humanity reaches for the stars and succeeds. But the numbers beneath that sentence tell a different story. They tell the story of a distance so vast that it swallows every speed humans have ever achieved, exhausts every fuel source we have ever harnessed, and outlasts every machine we have ever built. The stars are not hiding from us. They are simply operating at a scale that does not care about human ambition, human timelines, or human lifespans. And the speed problem, as staggering as it is, may not even be the hardest part. Every propulsion system humanity has ever used to explore space relies on the same basic principle. You throw mass out the back of your vehicle as fast as you can, and Newton's third law pushes you forward. Chemical rockets throw superheated exhaust gases. Ion engines throw electrically accelerated atoms. Even nuclear thermal rockets throw heated propellant through a nozzle. The differences between these systems come down to two variables: how fast they can throw that mass, measured as exhaust velocity, and how much energy they can extract from their fuel per kilogram. These two numbers define the boundary of what any propulsion system can achieve. And for interstellar travel, every system we have ever built falls catastrophically short. Chemical rockets, the workhorses that carried humans to the moon, and sent probes across the solar system, generate exhaust velocities of roughly 3 to 4.5 kilometers per second. The Space Launch System, the most powerful rocket NASA has built since the Saturn V, produces approximately 39 million newtons of thrust at liftoff. Impressive for escaping Earth's gravity. Irrelevant for reaching another star, a chemical rocket attempting to reach Proxima Centauri would need to carry so much fuel that the fuel itself would outweigh the payload by a factor that makes the calculation absurd. You would need a fuel tank larger than planets. The energy density of chemical propellants, roughly 10 million joules per kilogram for liquid hydrogen and liquid oxygen, is simply too low. Chemical energy comes from rearranging electrons in molecular bonds. That process releases only a tiny fraction of the energy locked inside matter. To reach interstellar speeds, you need to go deeper. You need to crack open the atomic nucleus. Before reaching for nuclear solutions, it is worth addressing a category of propulsion that generates significant public optimism, but fundamentally cannot solve the interstellar problem. Electric propulsion, including ion engines and concepts like the variable specific impulse magnetoplasma rocket, known as VASIM, represents a genuine advance over chemical rockets in one critical respect. These engines achieve far higher exhaust velocities, typically 20 to 50 kilometers per second for ion thrusters, and potentially up to hundreds of kilometers per second for advanced plasma engines. Higher exhaust velocity means more efficient use of propellant. A spacecraft can achieve a larger change in velocity for a given mass of fuel. This makes electric propulsion excellent for missions within the solar system, where travel times of months to years are acceptable and where the spacecraft can carry modest fuel supplies and accelerate gradually over long periods. NASA's Dawn mission used ion propulsion to orbit two separate bodies in the asteroid belt, a feat impossible with chemical rockets given the mission's fuel budget. The concept works brilliantly within its domain. The problem is thrust. Electric propulsion systems produce extraordinarily low thrust relative to the mass of the spacecraft. A typical ion engine generates a force measured in fractions of a newton, comparable to the weight of a sheet of paper resting on your palm. VASIM, in its most optimistic projected configurations, might produce several newtons. These engines accelerate spacecraft slowly, building velocity over months and years of continuous firing. For interstellar travel, this creates a devastating timeline problem. Even at the high end of electric propulsion performance, achieving 1% of light speed, roughly 3,000 kilometers per second, would require continuous thrust for decades. Reaching 10% of light speed, the minimum practical target for a human mission to Proxima Centauri, would require thrust durations of centuries and power levels far beyond anything an onboard reactor could provide. Electric propulsion trades thrust for efficiency, and that trade makes it superb for navigating the solar system and useless for crossing the gulf between stars. The engines that work best in our neighborhood are precisely the wrong tools for the journey beyond it. The energy requirements for a crewed interstellar mission deserve concrete illustration because abstract numbers, no matter how large, fail to convey the true scale of the problem. Consider a hypothetical crewed vessel massing 50,000 tons at departure, a figure at the low end of estimates for a ship capable of sustaining a crew of several hundred across a multi-decade voyage, including radiation shielding, life support, habitat modules, repair infrastructure, and fuel reserves for deceleration. To accelerate this vessel to 10% of light speed requires imparting a kinetic energy of approximately 2.25 times 10 to the 22nd joules. To then decelerate it back to orbital velocities at the destination requires removing roughly the same amount of energy. The kinetic energy alone for both maneuvers approaches 4.5 times 10 to the 22nd joules. That figure represents only the energy delivered to the payload. It does not include the vastly larger energy needed to accelerate the fuel itself, nor the energy for life support, food production, lighting, communication, navigation, or any other shipboard system across 4 decades of operation. To make that number tangible, Consider that the total energy output of every power plant on Earth, every coal station, every nuclear reactor, every hydroelectric dam, every solar panel and wind turbine combined amounts to roughly 5.8 times 10 to the 20th joules per year. The kinetic energy alone for a round trip of acceleration and deceleration is equivalent to roughly 78 years of total global energy production. But kinetic energy is only the beginning. A rocket must also accelerate the fuel it will burn later, and the fuel to accelerate that fuel. The rocket equation transforms the modest-sounding energy figure into an exponential spiral. Depending on exhaust velocity and mass ratio, the total propulsive energy budget can exceed the payload's kinetic energy by factors of hundreds or thousands. The fuel mass required for this mission could measure in the millions of tons. The ship would need to carry many times its own dry mass in fuel, and the fuel to accelerate that fuel, and the fuel to accelerate the fuel that accelerates the fuel. This exponential compounding is why no brute force approach to interstellar propulsion has ever produced a viable crewed mission architecture. Nuclear fission, the splitting of heavy atoms like uranium or plutonium, releases roughly 80 trillion joules per kilogram of fuel. That is about 8 million times more energy per kilogram than the best chemical propellants. This enormous energy density is why nuclear propulsion has been studied for interstellar concepts since the 1950s. The earliest serious design was Project Orion, conceived in 1958 by physicists Ted Taylor and Freeman Dyson at General Atomics. Orion proposed detonating nuclear bombs behind a massive pusher plate attached to the spacecraft. Each explosion would slam the plate forward, gradually accelerating the ship. The concept was mechanically crude but physically sound. Dyson calculated that an Orion vehicle using pure deuterium fusion detonations could achieve exhaust velocities of roughly 15,000 km per second and a delta V of 20,000 km per second, approximately 6.7% of light speed, yielding a flight time to Alpha Centauri of roughly 130 years. Later analyses of Telur-Ulam thermonuclear designs suggested top cruise velocities of 8 to 10% of light speed might be theoretically achievable if no fuel were reserved for braking. The catch, beyond the obvious political and environmental impossibility of launching a spacecraft by detonating nuclear weapons in Earth's atmosphere, was the scale of the vehicle. Dyson's interstellar Orion would have massed roughly 100,000 tons. It would have required millions of nuclear pulse units. The engineering challenges were staggering even by the standards of a civilization comfortable with nuclear arsenals. The Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space, effectively ended Orion as a practical program, though the physics remains valid. Project Daedalus, a study conducted by the British Interplanetary Society between 1973 and 1978, refined the nuclear pulse concept using inertial confinement fusion rather than fission bombs. Daedalus proposed igniting small pellets of deuterium and helium-3 using high-powered electron beams, creating controlled fusion explosions at a rate of 250 per second. The design called for a two-stage spacecraft massing approximately 54,000 tons at launch, carrying 46,000 tons of fusion fuel in the first stage and 4,000 tons in the second. Daedalus was designed as an unmanned flyby probe targeting Barnard's star, roughly 6 light-years away, with an estimated flight time of 50 years and a cruise velocity of 12% of light speed. It was never intended to slow down at its destination. It would scream past Barnard's star at 36,000 km per second, collecting data during a brief encounter window before continuing into deep space forever. Two details about Daedalus deserve emphasis because they illuminate the scale of the problem. First, the design required helium-3 as a fusion fuel, a substance so rare on Earth that the entire global supply would not fill a small room. The Daedalus designers proposed mining helium-3 from Jupiter's atmosphere using giant balloon platforms, an engineering project that would itself represent a civilization-scale undertaking requiring technologies we do not possess. Second, Even this extraordinary machine, burning 50,000 tons of exotic fusion fuel, could only achieve a flyby. It had no capacity to decelerate, enter orbit, or conduct extended observations. It was a bullet fired at the stars, fast, expensive, and unable to stop. The deceleration problem is one of the most underappreciated obstacles in interstellar mission design. Popular imagination tends to focus on the challenge of going fast. But going fast is only half the problem. If your goal is to arrive at another star system and do something useful, whether that means entering orbit, studying a planet up close, or delivering a human crew, you must also slow down. And slowing down from a significant fraction of light speed costs almost exactly as much energy as speeding up in the first place. For a rocket-propelled spacecraft, this roughly doubles the fuel requirement. You need fuel to accelerate, fuel to decelerate, and fuel to carry the fuel you will need later. The exponential mathematics of the rocket equation turn brutal. A ship that needs 50,000 tons of fuel for a one-way flyby might need several 100,000 tons for a mission that decelerates at the destination. The spacecraft grows. The fuel requirement grows faster. The engineering complexity grows fastest of all. Alternative braking methods have been proposed, including magnetic sails that use interactions with the interstellar medium to create drag and photon pressure braking using starlight at the destination. Each carries severe limitations that we will examine when we confront the full reality of arrival. For now, the essential point is that no proven deceleration method exists for a crewed interstellar vessel, and any solution that relies on onboard fuel roughly doubles the already staggering energy requirement. Fusion propulsion, the next logical step beyond fission, remains the most frequently cited hope for practical interstellar travel. Fusion reactions, the same process that powers the Sun, release roughly 3 to 4 times more energy per kilogram than fission and produce far less radioactive waste. A fusion-powered spacecraft could theoretically achieve exhaust velocities of 10,000 to 30,000 kilometers per second, depending on the specific reaction and engine design. At the upper end, this brings travel times to Proxima Centauri into the range of a few decades, for a flyby and perhaps a century or less for a mission that includes deceleration. The magnetic fusion plasma drive concept and various derivatives have been explored in recent papers as potential interstellar propulsion architectures, combining magnetic confinement with direct thrust generation. The problem is that controlled fusion remains one of the hardest unsolved engineering challenges on Earth. As of 2026, no fusion reactor anywhere in the world produces sustained net energy output. The ITER experimental reactor in southern France, the largest fusion project ever attempted, has faced repeated delays and cost overruns, with its deuterium-tritium fusion experiments not expected until 2039 under the most recently revised schedule. ITER is a stationary ground-based facility the size of a large building, supported by the combined resources of 35 nations, translating controlled fusion from a massive ground installation into a compact, lightweight, space-rated engine that can operate reliably for decades without maintenance, represents an engineering leap so vast that no credible timeline exists for its completion. Fusion propulsion is not a technology we are refining. It is a technology we have not yet invented. The gap between a ground-based fusion reactor and a flight-rated fusion engine deserves more attention because it is often glossed over in popular discussions, as though achieving sustained fusion on the ground automatically unlocks fusion propulsion in space. The two problems are related but fundamentally different. ITER, the most advanced fusion project on Earth, is a tokamak reactor that uses superconducting magnets cooled to near absolute zero to confine a plasma of deuterium and tritium at temperatures exceeding 150 million degrees Celsius. The tokamak machine alone will weigh approximately 23,000 tons. Its vacuum vessel alone stands over 11 meters tall and nearly 20 meters in outer diameter, enclosed within a cryostat nearly 30 meters across. It requires external power measured in hundreds of megawatts just to operate its magnets and heating systems, It is connected to cooling infrastructure, diagnostic systems, and support buildings that collectively occupy a campus the size of a small town. ITER is designed to demonstrate that sustained fusion can produce more energy than it consumes. It is not designed to produce usable thrust. It produces heat, which in a commercial power plant would be used to boil water and drive turbines. A fusion rocket requires something entirely different. It must convert fusion energy into directed exhaust momentum, ejecting reaction products at extremely high velocities through a nozzle or magnetic field configuration that channels the plasma in one direction. This is a problem of plasma physics, magnetic confinement geometry, materials engineering, and thermal management that is distinct from the problem of sustaining a fusion reaction in a stationary laboratory. A space-rated fusion engine must be compact enough to fit within a spacecraft, light enough to be accelerated to interstellar speeds without consuming impossible quantities of fuel, and robust enough to operate continuously or in repeated high-performance burn cycles for years without the maintenance infrastructure available on Earth. It must manage the neutron flux from fusion reactions, which degrades structural materials over time, without the ability to replace irradiated components. It must contain a plasma at temperatures hotter than the core of the Sun within a magnetic bottle that cannot fail, because failure means the plasma contacts the engine walls and the engine is destroyed. And it must do all of this in the vacuum of space, where waste heat cannot be conducted or convected away but must be radiated, requiring enormous thermal radiator surfaces that add mass and structural complexity. Every step from laboratory demonstration to flight hardware involves not just scaling but reinvention. The history of aerospace engineering is filled with propulsion concepts that worked on paper, worked in the lab, and then took decades of additional development before achieving flight readiness. Jet engines took roughly 20 years from first demonstration to reliable military service. Liquid-fueled rockets took 3 decades from Goddard's first flight to orbital capability. Fusion propulsion, starting from a baseline of no demonstrated net energy gain, faces an engineering development path that is longer and more uncertain than either of these precedents. Antimatter propulsion occupies the extreme theoretical end of the spectrum. When matter meets antimatter, the two annihilate completely, converting 100% of their combined mass into energy. This is the highest energy density physically possible, roughly 300 times greater than fusion per unit mass. A spacecraft carrying just a few hundred grams of antimatter could theoretically generate enough energy to reach a significant fraction of light speed. In practice, the challenges are almost absurdly severe. First, humanity's total production of antimatter across all particle accelerators over all of history amounts to roughly 20 nanograms, not grams, nanograms, billionths of a gram. Producing the quantities needed for propulsion, even a few grams, would require particle accelerator infrastructure thousands of times larger than anything currently in existence, operating for years at energy costs that dwarf the output of entire national power grids. Second, antimatter must be stored without touching normal matter, because any contact results in immediate annihilation. Charged antiprotons have been stored in magnetic traps for over a year in laboratory settings, and the ALPHA experiment at CERN recently trapped over 15,000 antihydrogen atoms simultaneously. Yet even these achievements involve quantities measured in trillionths of a gram, storing the grams required for propulsion in a space-rated container that survives launch vibrations, radiation, and thermal cycling for years remains beyond any engineering capability we currently possess or can reasonably project. Third, even if you could produce and store antimatter, harnessing its annihilation energy for propulsion is profoundly difficult. When matter and antimatter annihilate, much of the released energy comes in the form of gamma rays and neutrinos. Neutrinos pass through matter almost without interaction and are essentially lost. Gamma rays are extremely penetrating and require massive shielding to protect crew and equipment. Some estimates suggest only about 40% of the total annihilation energy could be practically captured and directed as thrust. The remaining 60% becomes waste heat and radiation that must be managed, absorbed, or simply endured. Even with the highest theoretical energy density in physics, the engineering realities cut the effective performance dramatically. Then there is the concept that captured the most public attention in recent years. Breakthrough Starshot proposed an entirely different approach. Instead of carrying fuel on board, the spacecraft would be accelerated by a ground-based laser array. A phased array of lasers combining to produce approximately 100 gigawatts of directed power would focus a beam onto a reflective light sail measuring roughly 4 meters across, attached to a gram-scale payload called a star chip. The photon pressure from the beam would accelerate the sail to approximately 20% of the speed of light within about 10 minutes, subjecting the tiny payload to accelerations on the order of tens of thousands of times Earth's gravity. At 20% of light speed, the craft would reach Proxima Centauri in approximately 21 years. Upon arrival, it would fly past the system at 60,000 kilometers per second, collecting data during an encounter lasting only hours before continuing into interstellar space. Breakthrough Starshot was elegant in its simplicity. By leaving the energy source on the ground, it eliminated the need to carry fuel. By making the payload tiny, it reduced the energy required to reach relativistic speeds. By abandoning any pretense of deceleration, it avoided the fuel penalty of braking. The design stripped the interstellar problem down to its most minimal form. Send something, anything, as fast as possible. Accept that it will never stop. Even this minimal version proved extraordinarily difficult. The laser array would need to produce 100 gigawatts of coherent, phased power, roughly equivalent to the output of 100 large nuclear power plants, focused into a beam tight enough to illuminate a 4-meter sail at distances of millions of kilometers. Laboratory demonstrations achieved phase locking with tens of lasers, scaling to millions of individual laser elements operating in coherent synchronization represents an engineering challenge with no clear solution path. The sail material must survive the beam without vaporizing, reflect nearly all incident light, weigh only grams across a 4-meter area, and maintain structural integrity under accelerations that would crush any conventional material. Research teams at Caltech and elsewhere explored ultra-thin silicon nitride membranes and produced small-scale prototypes, but a full-scale sail was never built. The Starship itself must carry a camera, a power source, navigation systems, and a laser communicator capable of sending data across 4.24 light-years, all within a mass budget of a few grams. As reported by Scientific American in September 2025, the project had entered indefinite hold after spending roughly $4.5 million of the originally pledged $100 million. After 9 years, Starshot had advanced understanding of individual component technologies, but had not produced an integrated prototype or a credible construction timeline. The project's challenges were not failures of imagination. They were collisions with engineering reality at a scale that $100 million could not begin to resolve. Multiple analyses suggested the final mission cost would fall in the range of $5 to $10 billion, and even that figure assumed technological breakthroughs in laser arrays, sail materials, and nanoscale spacecraft that had not occurred. And Breakthrough Starshot, to be absolutely clear, was never a human mission concept. It was the smallest, lightest, fastest possible version of reaching another star. A gram-scale probe on a one-way flyby. No life support, no radiation shielding. No food, water, air, or crew quarters. No deceleration, no return. Just a chip and a camera, thrown past the nearest star at a fifth of light speed, returning a few photographs during a flyby so brief that the entire Alpha Centauri system would cross the probe's field of view in a matter of hours. That was the version that proved too hard, the version that stalled after spending less than 5% of its budget, the version that the most optimistic projections placed decades away from launch. A human mission to Proxima Centauri requires everything. Breakthrough Starshot requires plus several orders of magnitude more. It requires a vessel large enough to sustain human life for decades. It requires propulsion powerful enough to accelerate that vessel, not a gram-scale chip, to a significant fraction of light speed. It requires fuel, either carried on board or delivered by external systems, sufficient to both accelerate and decelerate. It requires radiation shielding, structural integrity against interstellar dust impacts at relativistic speeds, and redundancy in every critical system. It requires all of this to function without failure for longer than any machine in human history has ever operated continuously. Let us be generous with the numbers. Assume fusion propulsion becomes a reality within the next 50 to 100 years. Assume a fusion drive achieves an exhaust velocity of 15,000 kilometers per second, roughly 5% of light speed. Assume a spacecraft can be built with a mass ratio that allows a cruise velocity of 10% of light speed, including fuel reserves for deceleration at the destination. At 10% of light speed, the journey to Proxima Centauri takes approximately 42 years. Add time for acceleration and deceleration phases, each lasting months to years depending on the thrust profile, and the total mission duration extends to roughly 45 to 50 years. That is the optimistic scenario, built on technologies that do not yet exist, assuming engineering challenges that have never been solved are solved within the coming century. Now consider a more conservative but still ambitious scenario. Nuclear pulse propulsion, the most physically validated high-performance concept, achieves a cruise velocity of 5% of light speed. The journey takes roughly 85 years. With acceleration and deceleration, call it 90 to 100 years. This is a multi-generational voyage. The crew that arrives is not the crew that departed. Their children might not even be the ones to see the destination. Their grandchildren might. At 3% of light speed, a speed that some engineering analyses consider more realistic for a large crewed vessel, the flight time exceeds 140 years. At 1% of light speed, which is still roughly 3,000 kilometers per second and far beyond anything we can currently achieve with a crewed spacecraft, the journey takes over 420 years. Each of these numbers assumes continuous, reliable propulsion, flawless navigation, and a ship that does not break down over timescales longer than most nations have existed. Each assumes the deceleration problem has been solved. Each assumes fuel, either carried or collected, is available in sufficient quantities. Each assumes the spacecraft can be built, launched, and operated at a cost that some human institution is willing and able to bear across decades or centuries of commitment. And each of these numbers applies only to Proxima Centauri, only to the nearest star. Every other star in the galaxy is farther. Most are incomparably farther. If we cannot reach the closest one within a practical mission duration, the rest of the galaxy remains untouchable. There is a concept in interstellar mission planning called the weight calculation, first formalized by researcher Andrew Kennedy in 2006. It addresses a paradox that haunts every proposed interstellar mission. If you launch a mission today using the best available technology, a faster mission launched decades later using improved technology will overtake you and arrive first. This means the rational strategy is always to wait for better propulsion before launching. But if you apply that logic consistently, you never launch, because there is always a theoretical future technology that could be faster. The weight calculation attempts to find the optimal departure date that minimizes total travel time, accounting for projected improvements in propulsion technology. Kennedy's analysis found that for most realistic technology improvement rates, the optimal departure date for an interstellar mission to Proxima Centauri lies roughly several decades to a century in the future. Depending on assumptions about how quickly propulsion science advances, the weight calculation is not a counsel of despair. It is a mathematical acknowledgement that the interstellar speed problem is not just about building faster engines. It is about the rate at which engine technology improves, the cost of premature commitment, and the strategic calculus of when to act versus when to invest further in research. A civilization that launches too early wastes resources on a mission that will be obsolete before it arrives. A civilization that waits too long may never launch at all, paralyzed by the perpetual promise of next year's improvement. This calculation matters because it reveals something the raw speed numbers do not. The interstellar distance problem is not a single engineering challenge with a single solution. It is a systemic problem embedded in the relationship between physics, engineering capability, institutional commitment, and time. Solving it requires not just a fast engine but an entire civilizational infrastructure. Energy production on scales we have never achieved, materials science we have not yet developed, manufacturing capabilities that do not exist, mission architectures that have never been tested, and sustained political and economic commitment across timelines that exceed the lifespan of most human institutions. We have trouble maintaining funding for space telescopes across 2 decades. The James Webb Space Telescope took 25 years from initial concept to launch. The International Space Station has been continuously occupied since 2000, but it requires regular resupply from Earth and has a planned operational lifespan of roughly 30 years. Neither of these achievements, extraordinary as they are, comes within orders of magnitude of the institutional endurance that a crewed interstellar mission demands. Suppose, despite all of this, that we solve the speed problem. Suppose a century from now, fusion propulsion is mature, laser sail technology can accelerate large payloads, or some combination of approaches yields a propulsion system capable of sending a crewed vessel to Proxima Centauri at 10% of light speed with the ability to decelerate at the destination. The journey still takes over 4 decades each way. Communication with Earth faces a round-trip delay of nearly 9 years. The crew is utterly alone, farther from home than any human beings have ever been, carrying with them everything they will need to survive for half a century in a vessel that must function without resupply, without repair shipments, and without rescue. This is where the conversation shifts from physics and engineering into something more fundamental, because speed was never the only problem. Speed is the most visible problem, the one that generates the most dramatic numbers and the most exciting technology concepts. But even if speed is solved, another category of challenge remains, one that cannot be addressed by faster engines or more powerful lasers, one that is rooted not in the distance between stars but in the fragility of human bodies, the limits of human psychology, and the finite reliability of every machine ever built. The propulsion challenge is staggering. It may take a century or more to solve, but it is, at least in principle, a problem of engineering and energy. The next problem is different. It is a problem of biology, endurance, and the hard truth that keeping human beings alive for decades in a sealed vessel between the stars may be harder than getting them there in the first place. A gram-scale probe does not eat, it does not breathe, it does not develop cancer from cosmic ray exposure, it does not suffer bone density loss, muscle atrophy, or cardiovascular degeneration. It does not experience loneliness, anxiety, depression, or the slow psychological erosion of knowing that every person it has ever loved is aging and dying 4 light years behind it. It does not need water recycling, carbon dioxide scrubbing, waste management, temperature regulation, or emergency medical care. It does not panic when a critical system fails. It does not grieve when a crew member dies. It does not need to reproduce, educate offspring, resolve interpersonal conflicts, or maintain social order across decades of confinement in a sealed metal container, hurtling through the emptiest environment in the known universe. This is the difference between a robotic mission and a human mission to Proxima Centauri. It is not a difference of degree, it is a difference of kind, and it may represent a harder barrier than propulsion itself. Begin with radiation. Interstellar space is saturated with galactic cosmic rays, high-energy particles originating from supernova explosions, active galactic nuclei, and other violent astrophysical processes throughout the Milky Way. These particles, primarily protons and heavier atomic nuclei, traveling at significant fractions of the speed of light, carry enormous kinetic energy. When they strike biological tissue, they do not simply pass through. They ionize atoms along their path, breaking molecular bonds, damaging DNA, and creating cascades of secondary particles that spread the damage to surrounding cells. On Earth, the planet's magnetic field and atmosphere provide substantial shielding against cosmic rays, while total natural background radiation from all sources, including cosmic rays, terrestrial radioactivity, radon gas, and ingested radionuclides, averages roughly 2.4 millisieverts per year. In low Earth orbit aboard the International Space Station, astronauts receive roughly 160 to 320 millisieverts per year depending on solar activity, partially shielded by Earth's magnetic field, which still deflects many incoming particles at that altitude. Even this reduced dose is tens of times higher than ground-level exposure. In interstellar space, beyond any planetary magnetic field, the full unshielded cosmic ray flux delivers an estimated dose of roughly 400 to 600 millisieverts per year, depending on solar activity cycles that modulate the local interstellar medium. Over a 40-year journey to Proxima Centauri at 10% of light speed, a crew member would accumulate a total dose of roughly 16 to 24 sieverts. For context, a single whole-body dose of 5 sieverts is considered lethal to approximately 50% of exposed individuals without medical treatment. 20 sieverts delivered acutely would be invariably fatal within days. The interstellar dose is chronic rather than acute, spread over decades, which allows the body some time to repair damage. But chronic exposure at these levels dramatically increases lifetime cancer risk, potentially by factors of several 100% above baseline. Studies of atomic bomb survivors and radiation workers consistently demonstrate that cumulative doses above 1 sievert significantly elevate rates of leukemia, solid tumors, cardiovascular disease, and cataracts. Doses above several sieverts cause measurable cognitive impairment, including damage to the hippocampus and prefrontal cortex regions, critical for memory and decision-making. NASA currently limits career radiation exposure for astronauts to levels that correspond to no more than a 3% increase in lifetime fatal cancer risk. Under the current standard, this translates to a universal career limit of 600 millisieverts for all astronauts regardless of age and sex. A 40-year interstellar transit would exceed this limit by a factor of roughly 20 to 40. NASA's own research, including studies conducted aboard the International Space Station and using animal models at the Brookhaven National Laboratory, has documented that prolonged exposure to heavy ion radiation, the most biologically damaging component of galactic cosmic rays, causes persistent neuroinflammation, accelerated brain aging, and behavioral changes in mice that have no therapeutic remedy. Shielding against galactic cosmic rays is fundamentally different from shielding against solar radiation or medical X-rays. Lower energy radiation can be stopped by relatively thin layers of dense material like lead or aluminum. Galactic cosmic rays, however, carry so much energy that when they strike dense shielding material, they produce showers of secondary particles, including neutrons and pions, that can be more biologically damaging than the original particle. This effect, called secondary particle production or spallation, means that adding conventional shielding can actually increase the dose received by crew members rather than decrease it. The optimal shielding materials for galactic cosmic rays are hydrogen-rich substances like water or polyethylene, because hydrogen nuclei absorb energy from incoming particles without producing as many dangerous secondaries. But effective shielding requires thickness. Calculations by NASA researchers estimate that reducing the interstellar cosmic ray dose by 50% would require roughly 20 to 30 centimeters of water-equivalent shielding surrounding the entire habitable volume of the spacecraft. For a crew habitat with an internal volume comparable to the pressurized modules of the International Space Station, roughly 900 cubic meters, the shielding mass alone could reach hundreds of tons. Every ton added to the spacecraft increases the fuel required to accelerate and decelerate it, compounding the propulsion problem we already examined. For a mission already pushing the limits of conceivable propulsion technology, adding hundreds of tons of radiation shielding may be physically impossible within any realistic mass budget. Some proposals suggest using electromagnetic fields to deflect charged particles, mimicking the protective function of Earth's magnetosphere. Conceptual designs for superconducting magnetic shields have been explored, but generating a field strong enough to deflect the highest energy galactic cosmic rays, particles with energies exceeding billions of electron volts, would require magnetic field strengths and coil dimensions far beyond current superconducting technology. The magnets would themselves add significant mass and demand continuous power to maintain superconducting temperatures near absolute zero for the duration of the voyage. No prototype has been built. No engineering study has demonstrated feasibility for a crude interstellar application. The radiation problem does not have a known solution. It has speculative concepts, each carrying penalties so severe that they threaten the viability of the mission they are meant to protect. Now consider life support. The International Space Station, the most sophisticated closed habitation system ever built, supports a crew of typically 6 to 7 people in low Earth orbit. It recycles some water and oxygen but depends critically on regular resupply missions from Earth. Typically 8 to 12 cargo deliveries per year from multiple providers carrying food, spare parts, replacement filters, clothing, scientific equipment, and other consumables. The station's environmental control and life support system has recently demonstrated the ability to recover approximately 98% of water from humidity, urine, and other sources, a milestone achieved in 2023 with the addition of a brine processor assembly. Even that 2% shortfall must be replenished from Earth. Oxygen is generated primarily by electrolysis of water, supplemented by supplies from cargo vehicles. Carbon dioxide is removed by a regenerable molecular sieve system that has experienced repeated component failures over the station's lifetime, requiring replacement hardware delivered from Earth. None of these systems operate without maintenance. Pumps fail, filters clog, seals degrade, sensors drift out of calibration. On the International Space Station, crew members spend a substantial fraction of their working hours on maintenance and repairs. They have access to a steady supply of replacement parts delivered from Earth. They can consult with ground-based engineering teams in near real time, with communication delays of only about 1 second. If a truly critical system fails beyond the crew's ability to repair, an emergency evacuation to Earth is possible within hours using a docked Soyuz or Crew Dragon capsule. An interstellar vessel has none of these safety nets. There are no resupply missions. No replacement parts arrive from Earth. Communication with mission control faces a one-way delay of years, making real-time troubleshooting impossible. A message sent from a ship halfway to Proxima Centauri would take over 2 years to reach Earth, and the response would take over 2 years to return. By the time advice arrives, the crisis that prompted the question has been resolved one way or another for 4 years. There is no evacuation capability. If the ship suffers a catastrophic failure, the crew cannot return to Earth. They cannot reach any other destination. They are alone in interstellar space with whatever they brought and whatever they can improvise from it. This demands life support systems that operate in a fully closed loop, recycling 100% of water, oxygen, and ideally food, with zero resupply for the entire mission duration. No such system has ever been built. The closest attempt was Biosphere 2, a 3.14-acre enclosed ecological system constructed in Arizona in the early 1990s. Biosphere 2 was designed to be a completely sealed, self-sustaining environment supporting 8 crew members. The experiment encountered serious problems almost immediately. Oxygen levels dropped dangerously low, eventually requiring external supplementation. Carbon dioxide fluctuated unpredictably. Many of the plant and animal species introduced into the system died. Insect populations collapsed, leading to pollination failures that reduced food production. The crew experienced significant caloric restriction and interpersonal conflict. Biosphere 2 demonstrated that creating a self-sustaining closed ecosystem, even on the surface of Earth, with unlimited external energy from the sun and the ability to abort at any time, is extraordinarily difficult. It remains the most comprehensive attempt ever made, and it failed to achieve full closure. Space-based food production adds another layer of complexity. Current experiments on the International Space Station have successfully grown small quantities of lettuce, radishes, and chili peppers in controlled growth chambers. These experiments demonstrate that plants can grow in microgravity and produce edible food. They do not come remotely close to demonstrating the ability to feed a crew. Growing enough calories to sustain even a small group of people requires substantial growing area, reliable lighting, water delivery, nutrient cycling, pest management, and harvest processing. Estimates for space-based agriculture capable of providing the majority of a crew's caloric needs suggest growing areas of several hundred to over 1,000 square meters. With continuous operation and zero crop failures over the entire mission, one bad growing season on Earth means higher prices at the grocery store. One bad growing season on an interstellar vessel means the crew begins to starve. Medical care aboard an interstellar vessel introduces problems that have no parallel in current spaceflight experience. On the International Space Station, astronauts have access to a limited medical kit, telemedical consultations with physicians on the ground in near real time, and the ability to evacuate a critically ill or injured crew member to Earth within hours. These safety margins vanish on an interstellar mission. The crew physician, if the mission carries one, must be prepared to handle every medical scenario that might arise across a population of dozens to hundreds of people over a span of 40 or more years. This includes trauma from accidents during maintenance work or equipment failures, acute surgical emergencies such as appendicitis or intestinal obstruction, cardiac events, strokes, dental emergencies that can become life-threatening infections if untreated, kidney stones, fractures, burns, and the full spectrum of chronic diseases that develop in any human population over decades, including diabetes, hypertension, autoimmune disorders, and cancer. Surgical capability in space remains rudimentary. Performing open surgery in microgravity presents immediate practical challenges. Blood does not pool in a wound. It forms floating globules that obscure the surgical field and contaminate the cabin atmosphere. Bodily fluids drift freely. Instruments must be restrained. The patient must be immobilized against a surface since there is no gravitational force keeping them on an operating table. Even if the ship generates artificial gravity through rotation, the Coriolis effects within a rotating habitat can cause nausea and disorientation that complicate delicate manual procedures. Current research into space surgery is limited to animal experiments and simulations. No human surgical procedure has ever been performed in space. The equipment required for a functioning operating theatre, sterilization systems, anesthesia delivery, blood supply and transfusion capability, post-operative recovery facilities, adds further mass and complexity to the ship's medical infrastructure. Infectious disease represents a particularly insidious threat in a sealed environment. The crew inhabits a closed atmospheric loop. Every pathogen that enters the system stays in the system. On Earth, infectious outbreaks are contained partly through spatial separation, quarantine facilities, and the vast reservoir of outdoor air that dilutes airborne pathogens. On a ship with a fixed atmospheric volume shared by all inhabitants, a novel respiratory infection could spread through the entire crew within days. Antibiotic-resistant bacteria, which evolve readily in closed environments where antimicrobial use is concentrated, could render the ship's pharmaceutical supplies ineffective against common infections. Studies aboard the International Space Station have documented that microgravity appears to enhance the virulence of certain bacterial strains, while simultaneously suppressing aspects of human immune function. A population living for decades in a sealed vessel faces the continuous risk of an infectious event that could incapacitate a significant fraction of the crew simultaneously, with no external medical support, no evacuation, and a finite, non-renewable supply of medications. The inability to evacuate a critically ill crew member changes the calculus of medical risk entirely. On Earth, and even on the International Space Station, there is always a fallback. A patient who cannot be treated locally can be transferred to a facility with greater capability. On an interstellar vessel, the ship is the only facility. If a crew member develops a condition that exceeds onboard treatment capability, the outcome is determined entirely by what the ship carries and what the medical team can improvise. There is no helicopter, no ambulance, no hospital ship waiting over the horizon. Every limitation in the onboard medical kit becomes a potential death sentence for conditions that would be treatable on Earth. The question of crew size compounds every life support challenge. A larger crew provides more hands for maintenance and repair, more specialized skills, greater genetic diversity for multi-generational missions, and more psychological resilience through social interaction. But a larger crew demands more food, more water, more oxygen, more living space, more medical capability, and more of every consumable and system. A smaller crew reduces resource demands but increases vulnerability. If a critical specialist, the only physician, the only engineer qualified to repair the fusion reactor, the only person who understands the navigation systems, becomes incapacitated or dies, the mission may fail regardless of how well every other system functions. Redundancy in human expertise requires larger crews. Larger crews require larger ships. Larger ships require more propulsion. The spiral compounds at every level. Mechanical reliability over interstellar timescales presents a challenge that has no precedent in human engineering. The longest continuously operating human-made systems in space are the Voyager probes, which have functioned for nearly 50 years. They are remarkably durable, but they are also remarkably simple by the standards of a crewed vessel. Voyager has no moving parts in its primary structure. It carries no life support. Its instruments draw tiny amounts of power from radioisotope thermoelectric generators that are slowly decaying. Several of Voyager 1's instruments have already failed. Its power output decreases by roughly 4 watts per year, and the mission team has progressively shut down systems to conserve what remains. By the mid-2030s, Voyager will likely lack sufficient power to operate any instruments at all. A crewed interstellar vessel is not a passive probe drifting through space. It is a city in a bottle. It has pumps, valves, compressors, heat exchangers, electrical distribution systems, computer networks, atmospheric processors, water purification systems, food production equipment, medical facilities, communication systems, navigation sensors, structural monitoring systems, and a propulsion system that must reignite perfectly after decades of dormancy for the deceleration phase. Each of these systems contains components that wear out, corrode, fatigue, or simply degrade with time. Seals crack, bearings wear. Solder joints develop microfractures from thermal cycling. Circuit boards accumulate radiation damage that alters their electrical characteristics. Lubricants evaporate or polymerize. Nothing lasts forever, and interstellar missions ask everything to last for a very long time. Terrestrial engineering addresses component failure through maintenance, inspection, and replacement. Cars undergo regular service. Power plants schedule shutdowns for overhaul. Aircraft are inspected after every flight and undergo major structural inspections at defined intervals, with any component that exceeds its rated lifespan replaced, regardless of apparent condition. All of this depends on supply chains, manufacturing infrastructure, and a workforce trained to produce replacement parts. None of this exists aboard an interstellar vessel. Every replacement part must be carried aboard or manufactured in transit. Carrying spares for every possible failure across a 40 to 100 year mission is a mass penalty that quickly becomes prohibitive. Manufacturing replacement parts in transit requires machine tools, raw materials, and fabrication capability that adds yet more mass and complexity. Three-dimensional printing offers some promise for in-space manufacturing, but current capabilities are limited to relatively simple parts in a narrow range of materials. Printing a replacement circuit board, a precision bearing, or a high-pressure valve seal requires capabilities well beyond current additive manufacturing technology. particularly in a space environment where microgravity, limited power, and constrained raw material feedstocks impose additional constraints. Even optimistic projections for in-space manufacturing do not envision the ability to produce complex, high-reliability components equivalent to Earth-manufactured parts within the timeline relevant to interstellar mission planning. The failure of a single critical system, one for which no spare exists and no repair is possible, ends the mission. Not in the dramatic, explosive sense of science fiction, but in the slow, grinding reality of a crew watching their air scrubbers degrade, or their water recycler lose efficiency, or their food production decline as grow lights fail one by one. The ship does not blow up. It slowly becomes uninhabitable. The margin between survival and death narrows with every component that cannot be replaced. And across 40 years, a great many components will reach the end of their functional lives. Human psychology in extreme isolation and confinement represents yet another barrier, one that is often dismissed as soft compared to the hard engineering challenges, but may prove equally decisive. Studies of crews in Antarctic research stations, submarine deployments, and simulated space missions such as the Mars 500 experiment, which confined 6 volunteers in a sealed facility for 520 days, consistently document significant psychological effects from prolonged isolation. These include depression, anxiety, interpersonal conflict, sleep disruption, cognitive decline, and motivational loss. The Mars 500 experiment found that several crew members became increasingly sedentary, experienced disrupted sleep-wake cycles, and showed measurable declines in alertness and cognitive performance over the course of the simulation. And that was 520 days, under 2 years, with the knowledge that the experiment would end and normal life would resume. An interstellar mission offers no such reassurance. The crew departs knowing they will not return to Earth for decades, if they return at all. Communication with friends and family becomes increasingly abstract as light-speed delays grow from minutes to hours to years. The psychological concept of an Earth connection, the knowledge that help is available, that someone is watching and cares, that a return is possible, erodes steadily as the ship moves deeper into interstellar space. After a few years of flight, the crew exists in a communicative void. Messages from Earth arrive years after they were sent, describing events and people that have changed beyond recognition in the interim. The crew cannot participate in life on Earth. They can only observe its ghostly echoes, delayed and increasingly irrelevant. Interpersonal dynamics in small, confined groups over long durations are poorly understood and inherently unpredictable. Research from Antarctic stations and submarine crews shows that even carefully selected, highly trained individuals develop friction, form cliques, and experience conflicts that can escalate to serious dysfunction. The shorter these deployments are, the more manageable the conflicts remain. Extend the duration to decades. Eliminate any possibility of crew rotation, personnel changes, or external mediation, and the psychological pressure becomes qualitatively different from anything studied. No data exists for human group dynamics in sealed environments over timescales of 10, 20, or 40 years. We are guessing, and the consequences of guessing wrong are fatal. The question of governance aboard a multi-decade interstellar mission is rarely discussed in technical literature, but may prove as consequential as any engineering challenge. Every human community requires systems of authority, decision-making, conflict resolution, and resource allocation. On Earth, these systems evolve over centuries, supported by cultural traditions, legal frameworks, enforcement mechanisms, and the implicit safety valve that dissatisfied individuals can, in principle, leave. On an interstellar vessel, no one can leave. The community is sealed, permanent, and inescapable. Whatever governance structure is established at departure must function across decades without the corrective pressures that shape terrestrial institutions. Who commands the ship? A military-style hierarchy offers clarity of authority and rapid decision-making, but risks authoritarianism over long timescales. when the oversight mechanisms of terrestrial military structures, congressional review, chain of command accountability, rotation of leadership are absent. A democratic model offers broader participation, but introduces the possibility of factional disputes, gridlock, or majority tyranny in a confined population where minority factions cannot withdraw or seek representation elsewhere. Hybrid models face the challenge of defining boundaries between technical authority and communal governance in an environment where almost every decision, from food rationing to reproductive policy to work assignments, has life or death implications. Leadership succession compounds the problem. A mission lasting 40 to 100 years will outlast any individual leader's functional career. The original commander may die, become incapacitated, or simply age beyond effectiveness. Transferring authority in a sealed, isolated community with no external arbitration is historically one of the most destabilizing events any society can face. Mutinies aboard sailing ships, power struggles in isolated colonial settlements, and succession crises in closed political systems all illustrate the risks. On an interstellar vessel, a succession crisis does not merely destabilize the community. It threatens the physical survival of every person aboard, because the ship's operation depends on coordinated technical management that governance failure can disrupt. The question of purpose is equally volatile. The founding crew departs Earth with a shared mission. They chose to go. They understand the stakes. Their commitment is voluntary and informed. But what about their children? What about the crew members who, 20 years into the voyage, begin to question whether the mission is worth the sacrifice? On Earth, people who lose faith in an institution can resign, relocate, or redirect their lives. On an interstellar ship, disillusionment has no exit. A crew member who no longer believes in the mission must continue performing their duties because the survival of everyone aboard depends on collective function. Forced labor in service of a mission one did not choose and no longer supports raises moral questions that no amount of pre-departure screening or psychological preparation can fully resolve. The longer the mission lasts, the more likely it becomes that the original unity of purpose will fragment, and the fewer tools the community will have to manage that fragmentation without coercion. Specific failures aboard the International Space Station illustrate in miniature what an interstellar vessel would face without resupply. In 2020, a small air leak was detected in the Zvezda service module, caused by cracks in a hull section that had been in orbit for 20 years. The crew spent months searching for the source of the leak, eventually locating and patching it with materials available on board. Had the leak been larger or in a less accessible location, the consequences could have been severe. In 2007, the station's computer systems in the Russian segment experienced a critical failure that disabled attitude control and oxygen generation simultaneously. The crew relied on backup systems and emergency procedures while ground controllers worked to diagnose and resolve the problem over several days. In late 2013, a coolant pump module failed in one of the station's external thermal control loops, requiring complex spacewalks over the holiday period to replace the unit with a spare that had been delivered by a previous cargo mission. In each case, the resolution depended on some combination of ground-based expertise available in near real-time replacement hardware delivered from Earth, or the ability to defer the problem until a resupply mission could bring the necessary components. Remove all three of those lifelines, and each of these incidents becomes a potential mission-ending event. The interstellar equivalent is not a station that can be gradually repaired and resupplied. It is a vessel where every failure must be resolved with what is already aboard, by a crew that may not include a specialist in the specific system that failed, using spare parts that may not exist, while the ground-based engineers who designed the system are 4 light years and 8 communication years away. The concept of a generation ship attempts to address the travel time problem by accepting that no single crew will complete the journey. Instead, a self-sustaining community lives aboard the vessel across multiple generations, with children born and raised in transit eventually arriving at the destination. This eliminates the requirement for any individual to survive the full journey but introduces a constellation of new problems. The ship must now support not just a crew, but a society. It needs schools, governance, cultural continuity, genetic diversity, sufficient to maintain a healthy population across generations, and reproductive rates carefully balanced against resource capacity. Demographic modeling suggests minimum viable populations for multi-generational space colonies of at least several hundred to a few thousand individuals, depending on assumptions about genetic management and social structure. A ship carrying thousands of people requires proportionally larger life support, food production, living space, and resource reserves. The mass and complexity of such a vessel dwarfs anything conceived in serious engineering studies. Generation ships also raise profound ethical questions that have no clear answers. The crew who depart Earth choose to leave. Their children, born aboard the ship, did not choose. They are born into confinement, born into a mission they had no voice in selecting, born into a society that exists solely to deliver a future generation to a destination that the founding generation will never see. Whether it is morally acceptable to create human lives under these conditions, lives constrained by the decisions of ancestors, lives with no possibility of ever visiting Earth or choosing a different path, is a question that philosophy has not resolved and engineering cannot address. Suspended animation or human hibernation is frequently invoked as a solution to long-duration spaceflight. If the crew could be placed in a state of dramatically reduced metabolic activity for the duration of the journey, the problems of food, water, oxygen, psychological stress, and interpersonal conflict would largely disappear. The crew would sleep through the transit and wake upon arrival, having aged only slightly. This is a staple of science fiction and a genuine area of scientific interest. It is not, however, a technology that exists. No human has ever been placed in a state of suspended animation and successfully revived. Therapeutic hypothermia, used in some medical settings to reduce brain damage after cardiac arrest, lowers body temperature by only a few degrees and is maintained for hours to days, not years or decades. Some animals, particularly certain species of ground squirrels, bears and frogs, enter states of torpor or hibernation that dramatically reduce their metabolic rates. Research into inducing similar states in humans has produced preliminary results in animal models, but the gap between cooling a mouse for a few hours and placing a human in suspended animation for 40 years is not a gap that current biology can bridge. The cellular damage from prolonged metabolic suppression, the challenges of maintaining hydration and nutrition during extended torpor, the risks of ice crystal formation in tissues, and the problem of muscle and bone atrophy during years of inactivity remain unsolved. Suspended animation is a hope, not a plan. It belongs in the category of technologies that might exist someday, rather than technologies that inform serious mission architecture. The cumulative weight of these challenges creates a distinction that most public discussions of interstellar travel fail to make clearly. Sending a tiny robotic probe on a one-way flyby past the nearest star is extraordinarily difficult. It has defeated every serious attempt so far, including a well-funded program backed by prominent scientists and billionaire investors. But it is a problem that exists within the boundaries of known physics and plausible near-future engineering. The challenges are severe but potentially surmountable with sufficient time, investment, and technological development. Sending human beings to the nearest star and keeping them alive throughout the journey is a problem of a fundamentally different character. It requires not just propulsion but an entire self-sustaining world, miniaturized into a vessel that must function with absolute reliability for decades in the most hostile environment accessible to human experience. It requires solving the radiation problem, the life support closure problem, the mechanical reliability problem, the food production problem, the medical care problem, the psychological endurance problem, and the social stability problem, simultaneously, with zero margin for the kind of iterative failure and redesign that characterizes every other engineering endeavor in human history. On Earth, we build, test, fail, learn, rebuild, and try again. Between the stars, the first failure may be the last. There is no iteration cycle when your laboratory is a sealed vessel 4 trillion kilometers from the nearest spare part. The propulsion problem asks whether we can build an engine powerful enough to close the distance. The human problem asks whether we can build a world durable enough to survive the crossing. These are not the same question. Solving one does not solve the other. And the human problem, unlike the propulsion problem, cannot be addressed by more powerful physics or more energetic fuels. It is constrained by biology, by the tolerance of human tissue and human minds, by the lifespan of pumps and seals and circuit boards, and by the hard reality that no closed ecosystem supporting human life has ever operated without external resupply for more than a few troubled years. But there is one more dimension to this problem that most analyses overlook. It is not enough to launch the ship, survive the transit, and arrive at the destination. The ship must also stop. And stopping, as we are about to see, may demand more of the mission than everything that came before it combined. Imagine the complete mission, not one piece of it, all of it. From the first bolt to the final breath. A spacecraft large enough to house a crew of perhaps 50 to several hundred people, depending on mission architecture, along with closed-loop life support systems, food production facilities, medical bays, repair workshops, raw material stores, radiation shielding, navigation systems, communication equipment, and enough redundancy in every critical system to account for decades of component failures without resupply. This vessel must mass somewhere between tens of thousands and hundreds of thousands of tons, depending on crew size, shielding requirements, and the propulsion technology employed. It must be assembled in orbit, since no rocket imaginable could lift such a structure from Earth's surface in one piece. The orbital assembly alone represents an engineering project larger than the International Space Station by orders of magnitude, a program that would consume decades and resources on a scale that no single nation or institution has ever committed to a space project. Once assembled, this vessel must accelerate to a significant fraction of light speed. At 10% of light speed, the target velocity for the most optimistic fusion propulsion scenarios, the ship travels at approximately 30,000 kilometers per second. Accelerating a vessel of this mass to that speed requires energy quantities that stagger comprehension. The kinetic energy of a 100,000-ton spacecraft traveling at 10% of light speed is approximately 4.5 times 10 to the 25th joules. For comparison, the total annual energy consumption of all human civilization is roughly 5.8 times 10 to the 20th joules. The energy required to accelerate the ship to cruise velocity is equivalent to roughly 77,000 years of current global energy production. Even with a fusion drive operating at theoretical peak efficiency, the fuel mass required dwarfs the ship itself by large multiples. Assume for the sake of argument that this energy problem is solved. Assume a fuel source exists, whether carried aboard, collected in transit, or delivered by some external system that can provide the necessary acceleration. The ship reaches 10% of light speed and enters its cruise phase. For approximately 40 years, give or take several years depending on the acceleration and deceleration profiles, this vessel coasts through interstellar space. During that time, everything we just discussed must function. Life support must cycle water, oxygen, and carbon dioxide without net loss. Food production must yield sufficient calories year after year without catastrophic crop failure. Radiation shielding must protect the crew against a cumulative cosmic ray dose that exceeds every safety limit ever established for human spaceflight. Every pump, seal, filter, circuit, bearing, and structural member must hold together far longer than its rated lifespan, or must be replaced using onboard manufacturing capabilities that do not currently exist. The crew must remain psychologically functional across decades of confinement in an environment more isolated than any human community has ever endured. And all of this must happen on the first attempt. There is no test flight for a crewed interstellar mission. The mission is the test. But arriving in the vicinity of Proxima Centauri is not the same as arriving at Proxima Centauri, and this distinction, which sounds pedantic, is actually the point where many interstellar mission concepts quietly collapse. A ship traveling at 10% of light speed covers approximately 108 million kilometers per hour. At that velocity, the known planetary orbits of Proxima Centauri, spanning only a few astronomical units, would be crossed in a matter of hours. If the ship does not decelerate, it performs a flyby. The crew gets a brief window, perhaps days at most in the outer system, perhaps hours in the vicinity of Proxima b, to observe the planet they spent 40 years travelling to reach. Then the system falls behind them, receding at 30,000 kilometers every second, and they continue into open interstellar space, with no destination ahead and no way to return. A flyby is not a mission. It is a glimpse. For a robotic probe carrying a camera and a spectrometer, a flyby may be scientifically valuable. For a human crew that has spent 4 decades crossing the void, a flyby is a tragedy. To actually enter the Proxima Centauri system, to orbit the star, to study Proxima b from close range, to potentially land on or interact with the planet, the ship must decelerate from 10% of light speed to orbital velocities. That means shedding virtually all of the kinetic energy it accumulated during the acceleration phase. The deceleration problem is not merely a mirror image of acceleration. It is in many respects worse. During acceleration, the ship departs from a solar system rich in infrastructure. It can be supported by ground-based or orbital laser arrays, assisted by solar energy, resupplied during the early phases of the journey, and monitored by communication systems with minimal delay. During deceleration, the ship is alone. It is approximately 4 light-years from Earth, approaching a dim red dwarf star with no infrastructure, no support, and no margin for error. Every joule of braking energy must come from systems aboard the ship itself, or from interactions with the destination environment that are speculative at best. If the propulsion system uses onboard fuel, the ship must have carried that fuel for the entire 40-year cruise, adding to the mass that had to be accelerated in the first place. The rocket equation punishes this mercilessly. For a ship that must both accelerate and decelerate using onboard fuel, the required mass ratio, the ratio of total initial mass, including fuel to final dry mass, increases exponentially. A ship that needs a mass ratio of 10 for a one-way flyby might need a mass ratio of 100 or more for an accelerate and brake mission profile, depending on exhaust velocity. Alternative deceleration concepts exist on paper. A magnetic sail, a large loop of superconducting wire generating a magnetic field that interacts with charged particles in the interstellar medium or the destination star's stellar wind, could theoretically provide drag without consuming onboard fuel. The concept is physically valid. Charged particles deflected by the magnetic field transfer momentum to the sail, gradually slowing the ship. But the braking force is small, and the deceleration phase could last years, requiring the magnetic sail to operate reliably across a prolonged period at the end of a journey during which every system aboard has already been operating for decades. The sail must be deployed, maintained, and controlled after 40 years of storage and cosmic ray exposure. No magnetic sail has ever been built, tested in space, or demonstrated at any scale. Another concept involves using the destination star's light as a braking mechanism. For a laser sail spacecraft, the sail could theoretically be reconfigured or split to reflect light from the destination star, using photon pressure to decelerate. This approach works more plausibly for small light probes than for crewed vessels, because the photon pressure from Proxima Centauri, a star with only about 1/1600% of the Sun's luminosity, is negligible against any payload massing more than a few kilograms. A crewed ship cannot rely on starlight for braking at Proxima Centauri. The star is simply too dim. The physics does not scale. Consider also what the ship encounters during deceleration. At 10% of light speed, every particle of interstellar dust becomes a projectile, A grain of dust massing 1 microgram, roughly the size of a fine sand particle, carries kinetic energy equivalent to a small explosive charge at 10% of light speed. The interstellar medium contains approximately 1 atom per cubic centimeter on average, along with sparse populations of dust grains. Over a journey of 4.24 light-years, the cumulative bombardment from these particles is significant. During the cruise phase, the ship's forward surfaces must withstand this continuous sandblasting. Various shielding concepts have been proposed, including sacrificial bumper shields that ablate under impact, electromagnetic deflection of charged particles, and strategic orientation of the ship to minimize cross-sectional exposure. None have been tested under realistic interstellar conditions. During deceleration, the ship must reorient to fire its engines or deploy braking systems, potentially exposing different surfaces to the particle flux or changing the geometry of its protective systems. Now layer in the operational reality. The deceleration burn, whether using fusion engines, nuclear pulse units, or some other system, must reignite and operate at full performance after sitting dormant or at reduced power for 40 years. No rocket engine in history has ever been required to restart after decades of inactivity. Turbopumps, injectors, combustion chambers, and fuel delivery systems are precision components that degrade over time, even in controlled environments. In the harsh thermal, radiation, and vacuum conditions of interstellar space, the expectation that a propulsion system will function flawlessly after 4 decades of dormancy is not conservative engineering. It is optimism verging on faith. If the deceleration system fails partially, the ship enters the Proxima Centauri system too fast to achieve orbit. If it fails completely, the crew flies through the system at interstellar velocity and continues into deep space forever. There is no second attempt. There is no rescue. The margin between mission success and mission catastrophe comes down to whether machines built by human hands, tested only under conditions available within our solar system, can perform their most critical function after the longest dormancy period ever demanded of any engineered system. Assume, against probability, that every one of these challenges is met. The ship decelerates. It enters orbit around Proxima Centauri. The crew, having survived 4 decades of cosmic radiation, closed-loop life support, mechanical attrition, and psychological isolation, arrives at the nearest star and looks upon Proxima Centauri b. What do they find? As of 2026, we do not know. Proxima Centauri b orbits within the habitable zone of its star, but habitable zone is a term defined by the possibility of liquid water, not by the presence of life or even a breathable atmosphere. Proxima Centauri is an active flare star. It regularly releases bursts of ultraviolet and X-ray radiation, powerful enough to strip an unprotected atmosphere over geological timescales. Whether Proxima b has retained an atmosphere depends on factors we cannot currently measure, including whether the planet possesses a magnetic field strong enough to deflect stellar wind particles, and whether its atmosphere was thick enough initially to survive billions of years of stellar activity. The planet is likely tidally locked, meaning one hemisphere would permanently face the star while the other faces perpetual darkness, though a Mercury-like spin-orbit resonance remains possible if the orbit is even modestly eccentric. Surface conditions would vary dramatically depending on the rotation state. Whether a circulation pattern could distribute heat to sustain habitable conditions is an open question in atmospheric modelling. Proxima b might be a living world with oceans and weather. It might be a desiccated rock scoured clean by stellar radiation. It might be something in between, partially habitable in a narrow twilight zone along the boundary between permanent day and permanent night. We do not know, and a crew that has spent 40 years reaching it will discover the answer only after every resource has been committed and every bridge has been burned. Pull back now and see the full picture. The mission requires orbital assembly infrastructure that does not exist, propulsion technology that has not been invented, energy budgets that exceed the output of civilizations, life support closure that has never been achieved, radiation shielding solutions that have not been demonstrated, mechanical reliability, across timescales that no engineered system has ever approached, psychological endurance under conditions that have no precedent in human experience, deceleration systems that must work perfectly after decades of dormancy, and all of this effort, all of this expenditure, all of this risk, targets a destination whose actual conditions remain unknown and may prove inhospitable to human presence. This is not a catalogue of reasons why interstellar travel is impossible. Physics does not forbid it. Nothing in the laws of nature prevents a spacecraft from travelling between stars. The speed of light is an upper limit, not a barrier at the velocities relevant to this discussion. Fusion energy is real. Nuclear reactions release the energy densities required. Materials exist that could theoretically be fashioned into the necessary structures. Biology, though fragile, is also adaptable. Human beings have survived in hostile environments before, from the frozen Arctic to the ocean floor in submarines to the vacuum of space aboard orbital stations. None of these facts are in dispute. What is in dispute, or what should be in dispute more honestly than it usually is whether the engineering gap between what physics allows and what human institutions can actually build, test, sustain, and commit to across the necessary timescales can be closed within any foreseeable future. Physics permits interstellar travel. Engineering has not achieved it, and the distance between permission and achievement is not a crack to be stepped over. It is a canyon that may take centuries to bridge. There is a useful concept in philosophy of technology called the difference between theoretical possibility and practical accessibility. A great many things are theoretically possible. It is theoretically possible to count every grain of sand on Earth. It is theoretically possible to build a tower from the surface of the planet to geostationary orbit. It is theoretically possible to disassemble Mercury and use the material to construct a Dyson swarm around the Sun. None of these things violate physics. All of them are so far beyond current capability that calling them possible without qualification is misleading. They are possible the way it is possible for you to walk from New York to Beijing. The path exists. The human body is physically capable of walking. But the ocean between you and your destination introduces practical barriers that transform a theoretical possibility into an effective impossibility for any individual standing on the shore. The nearest star is humanity's ocean. The path exists. The physics permits the crossing, but the crossing demands capabilities we do not have and cannot confidently project having within any timeline that responsible planning can address. We have not returned human beings to the surface of the moon since 1972. The Artemis program, designed to restore that capability, has faced repeated delays across more than a decade of development. We have never sent a crewed mission beyond the Earth-Moon system. We have never demonstrated closed-loop life support for more than short experimental durations. We have never operated a fusion reactor that produces net energy. We have never built a spacecraft capable of reaching even 1% of light speed. We have never tested any form of interstellar propulsion beyond small-scale laboratory demonstrations and computer simulations. Each of these represents a prerequisite for a crewed interstellar mission. None of them has been achieved. The terrifying reality is not merely that the stars are far away. Human beings have known that for centuries. The terrifying reality is that the nearest star, the closest possible destination, the one that sits at the very bottom of the distance scale, already exceeds every capability we possess by such enormous margins that even the most optimistic projections place a crewed mission centuries into the future. We are not close to reaching Proxima Centauri. We are not close to being close. We are standing at the edge of an ocean we have barely begun to learn how to cross, and the other shore is so distant that we cannot yet confirm whether it is even habitable. This is not a failure of human ambition. Human ambition is extraordinary. In a single century, we went from the first powered flight to landing on the moon. In a single generation, we built telescopes that see the edge of the observable universe, discovered thousands of exoplanets, detected gravitational waves from colliding black holes, and photographed the shadow of a supermassive black hole in a galaxy 55 million light-years away. We are a species that looks at the cosmos and refuses to accept that it is unreachable. That refusal is among our finest qualities. But ambition must eventually reckon with scale, and the scale of interstellar distance is not like the scale of any challenge humanity has previously faced. The gap between the longest journey any human being has taken, the Apollo missions to the Moon at roughly 1.3 light seconds away, and the shortest possible interstellar journey, to Proxima Centauri at 4.24 light-years, is not a gap that better rockets will casually close. It is a factor of roughly 100 million. Crossing it requires not just incremental improvement but civilizational transformation, new physics translated into new engineering sustained across new timescales, new institutional commitment maintained across generations, new solutions to biological and psychological challenges that we have only begun to identify, let alone resolve. Someday, perhaps, humanity, or whatever our descendants become, will cross that gap. Perhaps fusion drives will mature. Perhaps new physics will reveal propulsion principles we have not yet imagined. Perhaps artificial intelligence and robotic manufacturing will solve the reliability problem by enabling ships that repair and rebuild themselves in transit. Perhaps breakthroughs in biology will allow human bodies to withstand radiation, endure hibernation, or adapt to conditions that would kill us today. None of this is ruled out. All of it lies beyond the horizon of confident prediction. What we can say with honesty, grounded in the physics, the engineering, and the biology as we understand them today, is this. The nearest star is 4.24 light-years away. It hosts an Earth-mass planet in the habitable zone. These are confirmed observations. Every propulsion system that could plausibly reach that star within a human lifetime remains unbuilt and untested. That is confirmed engineering status. Keeping humans alive across the transit requires solving radiation, life support, reliability, and psychological challenges that have no demonstrated solutions. That is confirmed biological and institutional reality. Even the most modest interstellar probe concept ever seriously proposed, a gram-scale chip on a one-way flyby, has stalled after nearly a decade of effort. That is confirmed programmatic history. The stars are not unreachable, but the nearest one, the closest point of light beyond our sun, the one that every calculation starts with because it represents the minimum possible distance, remains beyond the practical capability of human spaceflight, by a margin so wide that closing it will likely be measured not in years or decades, but in centuries. You can walk outside tonight and look up. If you are in the southern hemisphere, you can find the constellation Centaurus and know that somewhere in that patch of sky, a small red star too faint to see with your eyes is orbited by a world roughly the size of Earth. That world is closer to you than any other planet, orbiting any other star. It is the nearest harbour in an ocean of emptiness that stretches across 100,000 light-years in every direction. And it is so far away that every machine humanity has ever built, every fuel we have ever burned, every speed we have ever achieved, falls short of reaching it by factors that make the crossing feel less like a journey and more like a physical law we have not yet been given permission to break. The terrifying part is not that the stars are distant. We have always known the stars are distant. The terrifying part is that even the closest one, the single nearest point of light in all the cosmos, may still sit beyond the practical horizon of human travel. Not because physics forbids the crossing, but because the crossing demands more than we have built, more than we can currently build, and perhaps more than we will be able to build for a very long time. That is not a statement of hopelessness. It is a statement of scale, and scale, in the end, is what the universe does better than anything else.